Kansas City SQL Server User Group. Thanks everyone for joining. We're happy to welcome David Klee, one of our favorite speakers, to our user group today, covering your assets when you blame your infrastructure for poor performance. For the audience, this session is recorded and will be uploaded to our YouTube channel. Once the recording is ready, I will place the link inside the Meetup event and post them far and wide on various social media platforms. If you miss any of those, you can always check out our YouTube channel to see our latest and greatest listings. And with that, I'm going to turn it over to you.
All right, thank you very much. This is Cover Your Assets when you blame when you blame poor performance on your infrastructure. We've all been there. You know everything's fine. Your infrastructure team is screaming. Nobody gets along. Nobody's nice with this kind of stuff. It's just one big blame game, big finger pointing match. Well, part of it is because we don't come from an infrastructure background. You may end up in a spot where you're speaking apples to oranges and they don't get what you're saying, and they may be speaking in terminology that you've never seen before. So this is a session on how to handle dealing with poor infrastructure performance. My name is David Klee. I am the founder and chief architect of HeraFlex Technologies. I'm lucky enough to be a Microsoft Data Platform MVP and a VMware vExpert. Contact info is up on the screen here. I have a lot of fun with this kind of stuff. I really do. The topic is fun. It's something I've been dealing with for a long time now. And I honestly spend probably half of every week just being the punching bag between infrastructure folks and data folks. So what you're going to get is just a lot of tips and tricks around what's actually under the hood. Why can this be problems? What are some terminology? What are some things you need to look out for to help really solidify your case that when things are slow, you give concrete, verifiable, backable data points on all the stuff that we actually care about. So what are we going to talk about tonight? One is baseline and metrics, absolutely critical, and it takes a subjective conversation and makes it a lot more objective, so that way people can't just argue away or try to explain away certain things. We're going to talk about networking, which arguably has a lot to do with this kind of stuff, and then CPU and memory and storage. And as I like to joke about them, it's the four main food groups of IT. Everything else just buzzwords, automation on top of it. So how many of you go to work on a Monday morning and people at your desk just corner you? It's slow. You got to fix it. Rah, 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 rah. It's got to be the database. Where are they coming up with the fact that it's databases? Well, that is simply because DBA doesn't mean database administrator. It means default blame acceptor. Everybody in IT blames database. We always blame security, and then everybody blames the network. It's just, it's a big finger pointing match, and everybody blames without making rational, objective measurements to be able to say it's actually this because we have this and this and this data point to go back it up. So here's the challenge. Bottom line, SQL Server gets blamed. Don't be like everybody else and just point the finger without data. This whole discussion goes back to being objective. What can you see? What can you measure? What can you get data points to go and actually point the direction, and not the finger, the direction as to what's going on? So we got to go back to the basics, and we got to figure out, of all the stuff that we manage, what has the data to help set that direction and get supporting information. And a lot of it is collecting a lot of this information. So one, if you see an infrastructure problem like this, you didn't do this. This is an infrastructure problem. The database administrator was still blamed when this happened. That was a $185,000 blade that went up in smoke. You think the DBA had anything to do with that? Nope. So we're going to start at the very beginning. SQL Server, item 0. Because guess what? Before you blame, is it actually SQL Server? You better be really confident that it's not the database before you start blaming the infrastructure. So it could be anything. locking, blocking, latches, super latches. I've even had some where the CPUs were going berserk because query parse and compile time was way elevated due to an application updates. Is it just everything at the query level is running sluggish because of lack of stats? Is it garbage that accompanies bad third-party application software? And that's literally what I spend 3/4 of my week dealing with. Anything else? I mean, literally go through this layer first. Is it SQL Server? And if you can comfortably say, no, nothing has changed, everything is running as normal, or other things are running, but we got all these data points, now we can start hitting the infrastructure. And that's where understanding the metrics really come into play. We have to get some objectivity into this whole thing. So when people call me out, it's slow, I hate that phrase because I don't know what it's doing when it's running fine. I don't know if it's been like this for months and they're just now calling me, or some bit was flipped last night and everything is now running slow. What changed? Do we have any details about the current situation other than it's slow? Could it be this report that I run at 8:30 in the morning normally runs in 30 seconds and now it's taking 5 minutes? Get as much details. And a lot of this involves training your users. Get them to give you as much detail as they possibly can rather than just it's slow and they throw it at you. The bigger piece to know is resource consumption trends. And I know that's a very generic statement. But for the systems that we manage personally over here, and that's some of ours and some of our customers, if it's a Tuesday at 6 o'clock at night, I know what they're doing. I've got a baseline. I know what these systems are supposed to be doing at that day of the week and that time of the day. And if something is way off spec, it's going to float straight to the top. So how do we get that? Get a baseline. This is one of those areas that every single place that I go, I ask for a resource consumption baseline and nobody has it. And when you start helping them produce it, people flip out. I spent 3 hours on the phone today going this with different environments. One was asking for a 64-core SQL server. We looked, they needed a 2-core machine. You don't need them that big. I need to know, what is this thing doing? What is it actually using? The whole it's slow thing is crazy. The whole purpose of the baseline is to tell me how the system is being used by the applications that are on there. Could be SQL Server, could be web servers, could be domain controllers, whatever. I need to know. I've been looking for third-party tools that can do this. There's arguably not a lot of great ones. And what's out there, the granularity is not good. So what it does is it doesn't really discern what a normal point in time is versus a normal day. And a lot of them don't even get detailed enough to tell you, is it during business hours or is it after hours? And it's a real challenge. So you have something built into Windows that you can use right now. You can use Windows Perfmon. Windows Perfmon, totally free, built in there. If you're on Linux, there's IOSAT and Systat, and I'm working on some automation for that. We released a PowerShell module a while back that allows you to automatically set up the Windows Perfmon collection to collect around the clock. And then PowerShell script, they can import it into a SQL server. You can run it nightly, free info here for how to set it up. Don't have any contact info required. Just go and have fun. This gives you a ton of performance information in the raw format that now we can plug in. T-SQL, Power BI, Excel, whatever you want to do, you now have this raw data and you can get a ton of really good information. All the counters, the way we like it set up, it's all in that document. It's just PDF, no info required. So enjoy and have fun. And when you get that information, look what you can do. I can visualize the stuff in a way that even a manager can understand it. You look at the chart, something's running at midnight. There's something running at 1. Everything's quiet from 2 to 3. Something runs at 3. 6 o'clock, people start logging in. Between 11 and 1, people go to lunch. And by 5:15, 5:20, that place is a ghost town. A real SQL server. Active, no strain, everything's nice and balanced. Picture says 1,000 words right there. This is an example of what you can also find with this. And this is quite literally my image of a dumpster on fire floating down Main Street in a flood. This is as bad as it gets. This was a virtual machine with CPU misconfiguration and SQL Server and Windows Standard Edition fighting it out for different bits of CPU time. It was horrible. It floats straight to the top once you have the raw data. You got to get the data because now I know what a normal day looks like. The next step, from a SQL Server perspective, just a free tip out there. If you've never dug into the Glenberry diagnostic scripts before, please do yourself a favor and do it. There are enormous amounts of phenomenal resources in those scripts. Tons of DMVs, and don't just ask what and just click through the scripts. Start to study them, because now sysconfiguration, process memory, DMOS node, sysinfo, virtual file stats, there's so much good information in there you need to study. You don't need to be able to rattle these things off the top of your head, but in the event that you're digging for challenges or for a lot of this information, you need to know what set of DMVs to go to. And with that, then we can start to figure out how can we collect a lot of the info that we care about? How can we prove or disprove it's not actually SQL Server with this? Quite literally today, I'm troubleshooting some CPU consumption where things are just imbalanced. And SysDMOS nodes, guess what? They had a 58-core SQL Server with SQL Server Standard Edition that could only use 24 CPUs. Right there, big imbalance. Not cool. Study, study, study. You don't have to be able to rattle these things off right off the top of your tip of your tongue, but you need to know what they do, why they do it, and how to use them. Okay. Now let's start diving into the network. And this is where things get pretty interesting. So one, if your server room looks like this, set fire to it. Don't, please don't. I saw this at a customer site. They allowed me to take a photo of this as long as it didn't have any identifying info in here, but I really wanted to walk through here with a pair of hedge clippers and just clean house. This was a disaster. This is not the kind of network. So if your network room looks like this, yeah, have a chat with them. The network, it sounds simple, but it's literally just how everything communicates. It could be storage network, could be regular communication network. It's just how everything communicates. Every server's got it. You need to know some basics. So step number one, TCP communications. This is how SQL Server communicates. It's lossless. So if you lose a packet, it does a retry in there. We need to know how this thing actually operates. You don't have to go crazy with it. But essentially, you have a payload and you have an acknowledgement. It's called an ACK. So essentially, you got two servers communicating. Server number A here is trying to send data to B. It goes, hey, here's a payload. Did you get it? And if the other side replies, yep, good, then it sends the next one. Sounds silly? That's literally what it does. There's an additional piece in here with UDP. That's lost, so you don't have to deal with that for SQL Server. Stuff that I care about there. Can it even get to B? Is it blocked? And how long did it take? If it can get there, but it takes 10 minutes to respond, you're going nowhere fast. If it can't even get there, we need to figure out why. So now, first thing we got to do, two machines trying to communicate. Can A figure out where B is at? Easiest way? DNS, domain name services. And what it's really doing is it's the thing that translates a computer name to an IP address. Can it resolve? So if you don't have communication through public cloud, wherever, NS lookup, and then a fully qualified machine name, what you're trying to get to. It tells you the domain controller that your computer is set to look at, and then it tells you if it can actually resolve the remote machine. And if so, what IP address does it come back to? Built into Windows, totally free, ready to go. If it can do this, now we can figure out, is anything listening at the endpoint? Applications listen for connections on ports. SQL Server primary port 1433, dedicated admin connection 1434, TCP endpoints for availability groups and mirroring 5022. If we can't see these ports, see meaning connect and use them, it might be blocked. There's also a thing out there called ping. It's not TCP, it's an ICMP packet, and it basically just says, are you alive? It checks the round trip connectivity back and forth, and that's it. If you can't see the endpoint, there might be a firewall involved or a network route or anything. All a firewall does is just say, block all traffic, and then you set up exclusions. So in a lot of cases, could be Windows, could be hardware firewalls, it could be network routing rules, could be all kinds of stuff. SQL Server, we're going to let 1433 in, but block SMB, SSH, web server traffic, whatever you want. We can allow this and be really segmented with it. So we can say server A, B, and C can connect to SQL Server, nobody else can. That's why in some of the environments that you may work in, you have to connect into a jump box in order to get to some of the SQL Server activities. And I'm all for it. Security was not meant to be easy. If you're in the cloud, they call them cloud security groups. They're nothing but fancy software firewalls. We need to know some rules. What's got to talk with what? So if server A talks to server B and B needs to talk to C, A should not be able to see server C. We need to know what services are listening. We need to know what services and ports things are actually communicating on. Otherwise, reject this. Cloud is locked down by default. On-prem is wide open by default. All of these things can add some overhead. You got to be careful with it. But if you can lock this stuff down to where only the stuff that should be calling SQL Server can actually get there, you end up with an inherently more secure environment. So start poking around with those, because if you have connection issues, those are the basics. You can ping, and it just says, are you alive? So it's literally just ping space in the remote machine. You can do it by IP, you can do it by the machine name if it can resolve, and then you get a response. Look at that time right there, 1 millisecond, less than 1 millisecond, 1 less than millisecond, number of packets received, percent loss. If you want to continuously ping, ping space -T and then the destination name. And it can just sit there and run. If you're ever interested, you can do this and record the output to a database table using XP Command Shell. Do it if you have to. I don't like XP Command Shell, but if you need to, it works. Now, we can see the remote machine. We can connect there. Is the port actually listening for a connection? So if we want to check to see if the port that SQL Server listens on is open, we can actually use the PowerShell command test net connection. Computer name, port, boom, connection succeeded. So that's a great sign. It means something is up and running on that port, and chances are it's SQL Server. So it gives us a really good bit of activity. Now, that checks connectivity, checks response time. It doesn't tell us how much data we can send end to end, and that's tough. But there's a free utility out there. If you go to iperf.fr, there is a compiled version of a little utility called iperf. It's compiled for Windows. They also have it on Linux. I use it to validate end-to-end network throughput. Now, it does not measure response time. It does measure throughput. So if you want a totally saturated network, this is a great way to do it. We have a how-to guide for how to use it out here. Just tell me you're not going to do this for long during production hours, because you could actually saturate a network and cause some problems. A little command line utility, you download it, put it on 2 machines. It can be here and in the cloud, can be between 2 machines in the same data centers, wherever you want to run it. iperf 3 is a compiled version. And the way to set up the listener for it is -S. So all it does is it just says server listening on a port. You can change the port if you want. You have all kinds of flexibility with it. On the other side, the machine you want to test from, iperf3exe, -C and then remote machine, -T for 10 seconds, minus capital P 10, meaning, because, you know, P means worker threads. Don't know why, but P 10, that means do 10 worker threads, because one might actually get tripped up by some Windows networking issues. So we're just going to try to really max this thing out. How much data can we get across the network at what average rate? I did a 10-second test in my test lab. Between 2 machines, I'm averaging 8.65 gigabits per second on a 10 gigabit network. That's pretty darn good. I think I was actually saturating the virtual machines before the network. I think we could have gone a little bit higher, but that's still really good. So it's a real quick way. How much throughput can we actually get? How much speed do we actually have available to us? And, you know, for a WAN connection, if you're paying for 200 megabit connection and you can do this and you get 50 megabit, they may not be giving you everything you're paying for. So go check it out. And if this is way low compared to what you're normally expecting, something's not right. Go talk to your networking folks and see what you can do. The next one, how many hops? And a hop could mean where you go from one network segment to another, or one physical switch to another physical switch. There's a lot of pieces involved in there. And if you're going to the cloud, there could be a lot of little segments and jumps in there. But you just run trace route, trace RT space server name. You can see it resolved. We've got an IP over a maximum of X number of hops. Boom. The machine I was coming from and going to were on two different network segments in the same physical network in my switch, my test lab. It traversed a gateway on the switch, jumped to a different network segment, and there you go. So 2 hops to get there. Nice and straightforward. Sometimes it's 1, sometimes it's 30, 50. Not very fun. If it's long, you have more pieces in there and more pieces that can generally slow it down. So double check all that. Now, by the way, if you're stress testing this stuff, or if this is a production server and you're doing high-speed backups or things like that, and people are complaining that the backups are running slow, there's a Windows setting you might want to double check. It's called receive side scaling. And what it is by default, Windows will only use 1 CPU total to handle all network adapter traffic. If it's a 10 gig network or above, you may end up saturating that network adapter before you max out or you may saturate the CPU before you max out the network adapter. Windows receive side scaling, it is from the Department of Duh. Tell Windows to parallelize the network traffic on more than 1 CPU. And guess what? You can speed stuff up. Why is this not a default? It's starting to on Windows Server 22, but prior to that, in a lot of cases, this was not enabled by default. You have to do 2 layers here. One is NetSH interface, TCP, set global RSS equal enabled. That sets this for the operating system as a whole. Do this in a maintenance window. There is a slim chance this might actually disconnect or reconnect your network adapters, so just do it in a maintenance window, you'll be fine. The next is per network adapter. So if you only got one, no big deal. Go into the driver settings of the NIC, go to receive side scaling under advanced, check to see if it's enabled. Sometimes it is, sometimes it's not. If it's not, even if you turn it on globally, this network adapter won't benefit from it. Go do that. This one probably blips a NIC, so just do it in a maintenance window and you'll be fine. Another one is really silly. If you've got random network interruption where just sometimes things just turn themselves off. Your network adapter may be so intelligent it can turn itself off to save power, because that's exactly what we want on a server. This is not a tablet. This is not a laptop. This is a production server. This should not be a default. Thank you, Microsoft. Please, in a maintenance window, turn this off. You would be surprised. I would probably say 70% of the on-prem servers globally have this set. And you'll just get random disconnects, or things like availability groups will try to fail over, SCIs will have issues, all because of just one little checkbox here. Let's save 3 watts of power and cause production outages. Welcome to my world. Another one, network congestion. I know it sounds crazy, but a lot of folks are running different data centers all over the country. Guess what? Those connections are not infinite. Production, real world stuff. I was troubleshooting this last week with a customer. Everything was slow. Turns out their data center was in Atlanta. Their users were in Denver, and they wonder why it was slow. And we looked at the connection between the two. They were 100% occupied. So everything was just super sluggish. This is real world. If you are in the cloud and you're operating from servers on-prem, look at your connection between the two. Your internet provider will be able to tell you the traffic patterns and utilization rates. Is it maxed out? If so, see what you can do. Why are you getting all the traffic and the congestion? It's not fun. It's not fun at all. Now, another one. If you go to the Glenberry Diagnostic scripts, there's a query on there on wait stats. When people see async network I/O waits inside SQL Server, the knee-jerk reaction is that there's a network problem. It might mean there's a network problem. What it usually means is the application at the other end of the connection simply cannot read data as fast as the SQL Server is trying to send it. Therefore, the SQL Server has to slow itself down to wait for the connection on the other end. Well, that's exactly where the screenshot came from. Some application server was running, I think, like 50 concurrent connections to try to pull some data, and the application server had one CPU and 4 gigs of RAM. And it was just absolutely just retching on itself. It's not fun. There's a free utility out at SP Who Is Active. You go to whoisactive.com, you can find a GitHub repo. Go check it out. It will tell you all the stuff that's running. It also says if there's a query that's running right now that is waiting on certain things, it gives you the wait information on there. Go check that out, because if you see this, it might be an app issue, and you can start to troubleshoot it that way. Okay. CPU is where things get even more interesting. If you pick a physical server today, you end up with the main board, and this is where everything connects to. So CPUs, network adapters, power inputs, memory, stuff like that. Biggest thing I care about on here, CPU sockets. Technically, the terminology is a CPU package. So in this particular case, we have a main board that's got 2 sockets. We've got some memory. They're kind of split up in there. I'll talk about that in a second. Inside the CPU package, you have a handful of processor cores. You've got a little bit of shared memory. Then you got a memory controller. So this is when they say I've got a 4-core CPU or a 16-core CPU or even a 128-core CPU. That's what's inside that little chip. It's not quite that easy, though. There is an architecture convention nowadays called NUMA, non-uniform memory access. And what you end up with is a memory and CPU distribution that's not exactly balanced for all workloads. And why I say that, what you've got here on that main board that you saw, there were 2 package sockets for CPUs, and directly connected to each one were banks of memory, so DRAM. If CPU package 0 needs to access a bit of data that's in memory connected to CPU package 1, it can do it. It's got to hop from CPU package 0 to 1 through its memory controller to the memory and all the way back. So if the memory is not local to the other CPU, it's a little bit of a delay in there. And I mean, we're talking nanoseconds, but it's still a delay. We got to be careful with it, because on this main board right here, technically the CPU and the memory that's directly connected to it is called a NUMA node, or non-uniform memory architecture. We need to make sure that the operating system, potentially any virtualization in there, and the SQL server are actually lined up with this split in there, or else you can end up with stuff floating all over the place, and it can slow you down. In addition to that, we have to deal with this thing called hyperthreading. And this is something that a lot of infrastructure folks generally don't really think about. All hyperthreading or logical cores are, think of it as the percentage of a CPU that is just sitting there. It could be waiting on memory, could be waiting on storage, and it's literally just hanging out. What Intel and AMD do is they present that spare time as another CPU. It's not as powerful as the main CPU. Infrastructure folks don't know this, so they may end up giving you this kind of stuff. And by the way, you go buy a virtual machine in the cloud, let's say it's 4 cores, you have a 2-core VM plus 2 hyper-threaded cores. Biggest crime of the 21st century, in my opinion. You end up in a spot where you're paying for X and you're not getting all of that horsepower. You gotta be really careful with that one. The stuff to check in here. Do a select star from DMOS nodes. You end up with a node ID, and in some of these machines, you may have 2, you may have 4. The stuff to look at here, node ID and memory node ID. In some cases, you can have a memory node ID that's the same, but multiple actual node IDs. You can have an online scheduler count that might not line up with what's actually presented. Do not trust the task manager. It lies to you. If the virtual machine CPU configuration has been messed up because of sysadmins, not intentionally, they're not going to do that intentionally, but if it's unintentional, you may end up with something that says, you've got 1 socket by 16 cores. And then you come in here, it's like, I've got 8 sockets, each with 2 cores. It happens. It lies to you. So go double check that. Automatic soft NUMA is another thing you got to watch out for. Starting in SQL Server 2016, if SQL Server detects more than 8 CPUs per NUMA node, it can automatically start subdividing this. So, the example I had earlier, earlier today actually, a customer had a computer. It was 2 sockets, each with 14 core CPUs plus hyperthreading. What they ended up with was an automatic soft NUMA split of 7 cores plus 7 cores on one NUMA node, and another 7 cores plus 7 cores. And it ended up in this really weird split because it didn't line up quite right because of some problems that they had with SQL Server licensing. So double check. You can check this when the machine starts up. Look at your error log. It's going to be right up at the top right there. If you see this, it's not necessarily a bad thing, but just be aware that if you have a 14 core machine and your max stop is set to 8, your max stop might actually just be 7. It might actually slow you down. So check for that. Another one, I saw this earlier today actually, core parking and power savings. If it's a physical machine or if it's a virtual machine that's misconfigured, your Windows power plan can be set to balanced. And what you'll find is that the base frequency of the CPUs could be half of what they're rated at, which means they run slower. And Windows can even park CPU cores, which means, yeah, we're just not going to use that one for a while. It slows you down. And SQL Server generally doesn't like that very well. So what you find is that if you set the Windows power plan to high performance, 1, it won't do that. 2, it won't even try to do that. And you end up maintaining some speed out of it. It's free. It's online. You don't need a maintenance window or an outage window to go do it. You can flip the switch there and life is good. Now, with the NUMA discussion, things get really interesting. And this is where education to your infrastructure team will really matter. The 2 settings we care about, cost threshold of parallelism, max degree of parallelism. When SQL Server receives a query, it parses and compiles a query, and it comes up with a statement subtree cost, which is essentially just a number of complexity. Higher means more complicated. No unit of scale there anymore. If that number for that query is higher than this value, then SQL Server will look at the max degree of parallelism to look at up to how many cores it can try to parallelize a query on. You have to be careful with this stuff because what you end up with is a state where if the NUMA information is spanning multiple NUMA nodes and somebody went in and set max degree of parallelism of 16 on a 2-socket 8-core machine, it may end up slowing you down. You got to be careful with it. There's no magic bullet with any of these things. That's the challenge. If you read blog posts out there, it says cost threshold must be 50 or 25 or 100. They're lying to you. They don't know what they're doing. It's workload specific. Dial this in. Max degree parallelism, if it's a relational system, maybe a lower max stop might actually help you. I'm not saying 1, but 2, 4, I've seen these all over the place and they're reasonable. Cost threshold for parallelism default is 5. In a lot of cases, that's too low. Not all, but a lot. And sometimes 25 works. Sometimes 50 works. I got one ERP system we do a lot of work with. 18 is the magic bullet. Be careful and tune these. See where you land, but try to get that workload in one NUMA node if at all possible. And then I know this sounds silly, but look for other garbage running on your SQL Server other than SQL Server. Sysadmins, security professionals, they love to load this stuff up with all kinds of extra garbage. Backup agents, other just management systems. I caught one where a remote access piece of software is eating 40% of the CPU time. You don't need any of that stuff. Check for all the other garbage running in the back. Lately, I found CrowdStrike, SentinelOne, Microsoft Defender. They don't have SQL Server antivirus exclusions built into them. So double check. They may actually be scanning the heck out of your machine all because they don't recognize the pattern that it's a database server. Double check. If you want to be a little more objective, in the Glenberry diagnostic scripts, there is a query in here. It's approximately 47, depending on what version you're on. You can end up getting the CPU information out of the ring buffers from sysdmos sysinfo. What you end up with is a state where you can say, give me the SQL Server.exe CPU consumption, give me everything else running in the background, and give me idle time. In a lot of cases, you may actually be able to catch that, hey, other stuff is eating 10 or 20 or 30% of the CPU time, whereas a SQL server is eating 5%. It adds up, and it gives you more data to be able to go to the infrastructure folks and say, this is what's going on. Something else is eating the CPU time. And quite honestly, I talked about perfmon at the beginning. You can actually capture all the running processes and their CPU or memory or disk consumption. You can be even more scientific about it. Now, virtualization, I'll touch on this for just a second. Bottom line, it's the new beige. If it's a server, it should be virtual at this point, in my opinion. The whole VMware thing has made life a little more interesting lately. It should be VMs. All the hypervisors are modern. They're mature. They all just work. The scheduling portion of the hypervisor is where a lot of infrastructure people don't know. And us as DBAs, we don't know this stuff. So I want to give you just a little bit of a background on what it's doing. All the hypervisor is resource and schedulers. That's it. If I get CPU, memory, network, disk under the hood on a physical server, all it is just a scheduling queue that says a VM, a compartmentalized operating system, and everything that's in it. And quite honestly, if you're a little more modern, a container is nothing more than virtualization without dragging along the operating system. That's it. All it says is any one of these servers that are running on the same physical machine can act like they're accessing any of these compute resources, but they have to go through the resource schedulers. And if something's not right, they start to stack up. And when they stack up, everybody suffers. So when you're, let's say, load up SSMS or ADS, hit go on a query. It looks like it just runs, right? What it's actually doing under the hood is in the hypervisor, there's a little tiny cost to get that command onto the hypervisor resource scheduler. And then it might just sit there for a little bit. If the hypervisor is really busy, it may take it a minute to get there. Minute meaning milliseconds at worst. But it's ready to run. They call it ready time. And then it starts to run. But that doesn't mean it can't be interrupted. These resource schedulers are not first in, first out. They're prioritized. And if somebody else is deemed more important, they can cut you off and you have to wait. When it's in this wait state, there's all kinds of stuff that happen in there. And there's different ways to measure this. But these are the things that your VM admins should know how to do. If they don't, you contact me. I'll educate them. There's a bunch of different wait states in here. And whatever hypervisor you're on, there's measurements and telemetry that you can get. And it shows you the amount of penalty imposed on this virtual CPU's task. While it's doing all of this, there may be efficiency losses, the whole power savings thing. Maybe it's running on a hyper-threaded core and the physical equivalent core is super busy. Could be all kinds of stuff. So this is why when it comes to virtual machines, we need to allocate what we need, not necessarily what we want. Because the goal, minimize the amount of time spent here. Not only does it help you speed up, because it's less for the hypervisor to shove through this stuff, but it's less impact on everything else around it. We need to make sure that the amount of overhead here is just not that bad. So if you're on-prem, ask your sysadmins for the metrics. They can get this to you if they want. If they don't want to, you contact me and I'll no strings attached. I'll yell at them for you. The challenge is if you're in the public cloud, it's still VMs. Even if you're using, X as a service, it's still a VM with automation on top of it with limited visibility. You can't see any of this. You can feel it, you can measure, you can't see it. It drives me mad, but it's one of the trade-offs with the cloud. They say, well, you shouldn't need that. It's like, well, I say if you were doing your job right, we wouldn't need it anyway. It's interesting. We got to make sure that we line this stuff up. So we got the individual overhead of the VMs. Now we've got to make sure that the workload itself lines up with the physical hardware. So let's just say physical machine, 2 socket, 12 core, 128 gig of RAM per socket machines. Good machine. If my VM is small enough to fit inside one physical CPU socket, like this one, 10 core, 64 gig of RAM, no problem. Build it for one socket by 10 core, 64 gig of RAM. The hypervisor is going to essentially just park it on one of these. Everything is local to the NUMA node, and life is good. If the VM's bigger, let's say 16 core, well, 16 doesn't fit inside 12 too well. Chop it in half. 2 socket by 8 core, 128 gigs of RAM gets split into 2 by 64. And guess what? The hypervisor is going to split it and keep them there. And this awareness of this split is presented into the guest operating system, which then SQL Server picks up on, and you end up with a performance gain. And these are things you'll want to work with your sysadmin on, but you can find the kind of CPU that you're on from Windows Task Manager. In 2 seconds on Google, you can figure out how many cores it's got. If it doesn't line up, go to them and say, we need these to align because it's going to help with speed. Memory is the next big one. This is a common point of contention for sysadmins out there. Just point blank, it is. The sysadmins always love to say, you're not using all of that memory on the SQL Server, so we're going to take it all back. It doesn't work like that, but all it does is make ticked off DBAs. It's not fun. I hear this, every couple of weeks out of folks. They don't know what SQL Server is doing, point blank. I'm not faulting them. They have misleading telemetry. A lot of their telemetry is not really built to be application aware. So anything like SQL Server or other DBMSs or applications with a large memory footprint, they do their own memory management and not rely on the operating system to do it. And guess what? What it really means is the application telemetry that they're looking at doesn't show up right. So, on a SQL Server with 128 gigs of RAM, it might say you have 10 gigs of RAM that you're using. What it actually is showing is the amount of memory read from or written to that machine in the last whatever polling interval their tool samples at. It's incredibly misleading. This is the argument that they use. What you have to do is you have to go to them and say, yes, SQL Server has a big memory footprint, but guess what? You end up in a spot where things just aren't that good. You end up in a spot where they can say this. You're using it. You can demonstrate it. You can't just look at the memory footprint of the SQL Server executable. You have to get in the DMVs. You have to demonstrate how the stuff is actually being used. It could also be some other stuff on the machine. So all the security tools we talked about, they have a memory footprint. Analysis services, if somebody installed it by default and you're not using it, it claims 25% of what's in the available operating system at its startup time. SSIS, SSRS, totally variable. And there's all this other junk that's just installed in these machines. There's also random application usage patterns that can just wreck your day, especially some of the antivirus stuff. So just be really careful in there. But if you can demonstrate page life expectancy, memory grants, pending buffer cache hit ratio, latching, locking, all of the different weight stats, you can demonstrate how the memory is being used. And just a little bit of education, they might actually listen to you. Leave headroom in here for the operating system. 75 to 80% of the buffer pool for the operating system. It's a good starting point, unless you've got other stuff in the background that you're aware of. Use perfmon or whatever other monitoring tools you've got to watch for other applications really trying to intrude in that memory space. If you have enabled lock pages in memory, SQL Server will not, quote, budge on the memory request. So if it's squeezing windows, and lock pages memory is set, you may end up in a spot where things can get a little unstable. If you're doing high page file utilization, you may want to look into that as well. Leave enough header in there. In almost all cases, everything's just fine. But the metrics that we care about, there's the available memory counter under perfmon itself. We need to know how much memory is actually used by each process. And you can actually sample this with all running programs that are processed in the perfmon. Page file percent utilization and current size. It tells you if something is really spilling into virtual memory. And then because SQL Server's memory footprint is mostly a storage read cache, I want to know what the storage itself is doing. So show me disk reads per second, or read IOPS, and read bytes per second, and convert it to megabytes per second. But if you see that your memory footprints in SQL Server are extremely low, and we see a decent amount of page file utilization, but then you see disk reads and disk read bytes are just off the charts high, yeah, you're starved for memory and you're reading disk like crazy. Just interesting stuff that always comes from it. In the DMVs, there's a ton. SysTMOS process memory is probably one of the big ones. It shows you the SQL Server memory footprint. It shows you what all you have locked. It shows you if you have large memory pages. And if you have a SQL Server with a lot of RAM and you're running enterprise, you may want to look into it. It shows you percent memory utilization to the OS. It's got some counters that call process physical memory low. They almost never trip unless you're just so bad it's not even funny. But to look at the amount of RAM allocated to each of these little segments, that's really interesting, and it tells you, are we actually using all the RAM that we've got? If you're running Hyper-V, there is a setting out there called dynamic memory. I generally don't recommend it for SQL Server because it's basically, I've got 50 gigs of RAM, but I'm only going to turn on 20 of it until you start asking for more. I don't use this for production SQL Server workloads. And if SQL Server has lock pages and memory enabled, it could try to contrast and bump into SQL Server, which isn't going to give any of it back. And bad things happen at that point. It's not fun. Storage is another big one. I cannot stress this enough. The speed at which you can access the storage matters. But not all the metrics line up the way a lot of the infrastructure folks think about this. You've got three main metrics when it comes to enterprise storage. You have latency. In my opinion, this is arguably the most important. It's the round trip time to do something with the storage. Cheap storage does it in milliseconds. Good storage does it in microseconds. There's IOPS, or I/O operations per second, and it's essentially a rate of demand. Storage that can handle higher IOPS is better, but I just need this to be able to do more than I'm asking. I don't have to have this do anything crazy. And then there's throughput, or megabytes per second. And all it is IOPS times block size. The thing you really got to worry about here is interconnect throughput, because if I do a large block size and I'm slowing this thing down, I may end up saturating a network adapter or a fiber adapter. Latency matters the most, especially when we need to actually save a transaction. That adds up. The storage mediums that these things are on make a big difference as well. Spinning disks are out there. They've been out there forever. They're going to be around forever. They're cheap. They're slow. They have a real high capacity. There's flash drives, or SSDs. They're not so cheap, but really good latency. They're a lot better for random I/O. They still have the controller from a spindle drive on them, though. Not that good. And then a while back, they came out with a new standard called NVMe, or Non-Volatile Memory Express. They're not cheap. They have extremely low latency, and they are fantastic for random I/O. Ideally, this is where you want to be, but if the workload doesn't demand it, do you get much from your bang for the buck with that? So when it comes to cloud, you can provision different kinds of storage. Azure calls the spinning disk standard hard drive. Ignore them unless it's literally archival data that nobody ever looks at. Now, I'm guessing at what the hard drive types are out there. You've got the list. I don't know if it's spindle or SSDs. I'm guessing based on the performance characteristics of them. The standard SSD, pretty darn solid for a lot of workloads out there. High performance stuff, maybe. Premium SSDs feel like NVMe drives just based on their performance characteristics. Now there's premium SSDs V2 that just came out, and then ultra SSDs. Realistically, you're going to hit the ceilings that come along with the virtual machine and the cloud VM scale. I generally ignore those unless you really, really, really need it. And the VM is massive, so big that you don't have a lot of these other limits to work around. If you're using Azure Blob Storage, which I love to do for SQL Server backups, we don't know what it is. We just know it's faster than what we can actually push data there too. So that just kind of does its own thing. It's fine. I prefer premium SSDs for most of the workloads that we deal with out there. It seems to be a good bang for the buck. It seems to be a pretty darn good performer, all things considered. Now, the stuff you got to watch out for on-prem and in the cloud, it's latency. Talked about that a minute ago. With Perfmon, you can sample it. And you can see in this particular environment, the read latency was honestly not bad. You know, we had most things at 1 millisecond or under, and then the SQL Server data drives, yeah, little blips up to 8, 10, 12 milliseconds. It's not the worst. Write latency, good luck. My red line for writes and reads is 10 milliseconds sustained. This particular environment, it would be kind of like you're in about a 1982 Pinto. Not good at all. The SQL Server was absolutely struggling. You don't want to be there. And what was happening was they had under-provisioned the virtual machine scale, and they were hitting these IOPS so aggressively, these IOPS ceilings, that the cloud platform is slowing them way, 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 way down. Not fun. Those are my red lines. If you're on okay storage, 25 milliseconds for reads, still 10 milliseconds for writes. If you're on good storage, 10 milliseconds or less, ideally a lot lower than that. Part of the reason we hit these ceilings is the way the cloud providers and arguably regular SAN vendors on-prem deal with block size. This is a hard one. So if I'm trying to read a 1 megabyte file and I'm reading in 4 kilobyte segments, I have to do 250 calls to disk to read the 1 megabyte file, 250 IOPS. If my block size to read is in 1 meg, and if that file lined up with that 1 meg segment, I can do 1 IOP to read the exact same thing. But you can't just say, give me a 20 gig IOP, because then you end up reading everything all the time that you don't need. So there's a balancing act in there. The performance ceiling on this stuff matters. If you're on-prem, maybe the SAN can't handle a lot of those kind of things. Maybe there's interconnect speed that can't handle it. There's hypervisor and physical machine QDEFs. There's all this stuff going on around it. The cloud is where you see this the most. It's one of my biggest complaints with the cloud. There's storage demand ceilings placed on the virtual machine scale, the service scale, the criticality tier, the virtual disk type, the virtual disk size, and all the background stuff that's going on out there. It's not fun. You can actually see this. If you look at the virtual machine disk measurements, the resource ceilings that are listed out there, you can see here on Azure, 1 terabyte virtual disk, Azure P30, you have a 5,000 IOP or 200 megabyte per second sustained ceiling on this thing, and it enforces them strictly. You have to be careful, because if what you're coming from, let's say you had an 800 gig database, you only needed a terabyte drive, but you're demanding 8,000 or 9,000 IOPS on-prem, and you go to the cloud, boom, instant performance bottleneck. Or you're doing backups. You used to be able to do them at 800 megs a second. Now you got 200. Slows you way down. It's not fun. Those ceilings are pretty brutal. There is a little bit of caching that you can do in some cases for reads. Don't do writes underneath a lot of this stuff. Don't bank on it. We'll just put it that way. You can also see some of the ceilings out here depending on the scale. So premium SSD, higher scale than standard SSD, ultra disk. You've got really, really high throughput ratings and IOPS, but if you take a look at the virtual machine scale, guess what? You're in trouble, because let's say I don't need a monster VM. Let's go with a standard D8 SV5. So 8 core, 32 gigs of RAM. I can do 16 disks, but I have a maximum uncached throughput at 600 megs a second. No, 290 for the 8 core. If my disk has a cap at 200 megabytes per second and I attach 2 of them, combined the disks can do 400 megs a second, but the VM slows you down to 290. Same thing with IOPS. backfires. It backfires quick, especially with high performance machines. So you have to keep into account all this stuff. And from your perspective, the symptoms are high latency in guest. If you just see an IOPS spike that goes up or a throughput spike that goes up, and then your latency just shoots through the roof, that's what's happening. They're slowing you down. It also comes back to the block size calculation. This is, again, another one of the things that really just drives me nuts out here. You don't have to take my word for it. There's two links right here, one on Azure, one on AWS. Microsoft Azure treats disk block reads in a larger base block than you might think of. So if I'm reading a database table and the data is kind of scattered around, if I need to read, let's say, 4 database pages, so 4 8K blocks. If the NTFS file system is formatted as 64K, I'm now reading 3 64K blocks. The stuff underneath does it in 256K segments. So if they're not close to each other, instead of reading 24 kilobytes, I'm now reading 768 kilobytes in terms of the way they measure it. 1024 kilobytes is a megabyte. If I have 210 megabyte ceiling, how many IOPS is that? Not a lot. You may end up hitting these performance ceilings a lot quicker than you might realize, all because of the way that the base block is formatted versus the way the SQL Server layer is expecting it. And if you did a 4K default block, you're going to be hitting those even sooner. It's not fun. AWS treats it a little bit differently. They treat it as a 16K base block. So if you format these to a 64K, you may end up with a little bit better expectation on there. Just test this. Do a little bit of disk perf testing. You can see this clearly in there. For SQL Server, I use a 64K base block. Microsoft recommends it. I've been testing it for a long time. This seems to be kind of the sweet spot with the way SQL Server treats it versus the way the cloud and a lot of the infrastructure stuff actually do. You can tell this, fsutil, fsinfo, ntfsinfo, and then a drive letter. You can tell this on any machine that you're on right now. So go test this. Maybe your sysadmins didn't get this right. Look at bytes per cluster. It should be 64K. Another one that I like to do with big drives is bytes per file record segment. The default is 1K. It's the block size for the NTFS metadata pointers for everything on the disk. Format it with a /L, and you end up with a 4K block instead of 1K, which means there's 4 times less pointers for Windows to manage. You end up in a spot with, with these big drives with a lot of activity in there, you get a little bit better performance. It's destructive if it wasn't set like this at default, and they hardly ever are. Don't take the time. Don't waste the time to go reformat and move stuff around. It's a pain. But for new machines, highly recommended. Now, you've got disk latency. It's a single leading indicator when there's a problem with underlying storage just not being able to keep up or being slowed down by a cloud provider. SQL Server's got its own measurement of how to actually track latency. It calls itself disk stall. It's not the same thing as disk latency. It's a little bit different. SQL Server measures it by database data in log file. The Glenberry diagnostic scripts have a measurement in there, but it unfortunately is the average since the last time you rebooted. So if you're running backups in the middle of the night, or if there's a lot of congestion in there, you may end up in a situation where these are skewed. So I got a link out here at my blog. Go check it out. It might actually help you because it's how to sample this stuff ongoing. So if you see a big spike in the middle of the night when backups run, but the middle of the day is actually okay, you may end up being okay. Whereas some of the law of the averages will actually tell you something's really, really wrong. So if you put this next to disk latency as seen by Windows or Linux, and then put that next to whatever the cloud or the hypervisor telemetry is telling you, and then put that next to the telemetry the storage, the SAN is giving you, you can start to get some end-to-end data points. And if you see good, 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 way bad, something's not right in between there. It's probably not the SQL Server. you can see this clearly. This was an environment where somebody had actually misconfigured their virtual machine backups. They set it to run at 11:30 in the morning instead of 11:30 p.m. Boom. The latency on the SQL Server was skyrocketing for about 2 hours a day. That's bad. Easy to catch if you know where to look, but all they knew is 11:30 to about 1:32, everything in their environment would run slow. They had storage contention and a hypervisor and some networking problems. That added up fast. Graph the data. You've got it available. Do it. So I know we touched on a lot of stuff. We basically said benchmarks matter more than every single thing you can possibly do because it gives you the ability to defend against this stuff. And then went through the 4 main food groups, starting with network, CPU, memory, and storage. Whatever you do, any changes you make, question everything, test everything, have objective data behind it, and have a baseline, because if you go to make a change, measure, make the change, remeasure. If everything looks good or better than was, life is good. And I think we'll open this up for questions.
Excellent. Thank you so much, David. Really appreciate it. So much information to consume. I'm excited to my network guy may hate you tomorrow, but
bring it on. I love it. I love arguing with the networking folks because at the end of the day, they're trying to defend themselves because they don't have the data to back up their claims. And now you've got the data to back up yours. And more times than not, you end up with somebody going, oh, yeah. So much fun.
Have you seen anything, kind of talking about performance hits, have you seen anything like with I'm drawing a blank here, with availability groups causing performance problems?
Yeah. I mean, essentially, the biggest thing with availability groups is that you do a remote commit on a synchronous secondary before you do a local commit. SQL Server 22 has an option there that says this number of remote synchronous secondaries have to commit before you continue, but it does a remote commit, then it does a local commit. So there is a performance wedge in there. If the networking that you have is really, really, really good, it's not that big of a deal. It might be a few percent. If the networking between the availability group replicas is terrible and your storage is really good, so let's say the storage has a 1 millisecond response time. If the network has a 10 millisecond response time, you've now just gone from 1 millisecond to 11 milliseconds. And that adds up. So that ping test that I showed you really helps. The problem with ping is that it's not granular enough. It basically, it's stupid. It's less than 1 millisecond. If you're on Linux, you can do down to the 3 decimal points. And most of the time, good 10 speed or 10 gig and plus networking is like 0.1.5, 0.2 milliseconds. And, for availability groups, it adds up, but it's not that big of a deal. It's usually a couple percent, give or take. It's not that big of a deal. There's definitely something there. It's usually measurable. It's really not noticeable. So if something's not right, watch out.
Yeah, I saw an interesting thing. We were trying to figure out like why two of our servers have differences. And some of it's kind of known, but one of the things that I saw that was interesting, because you had mentioned Glenn Berry scripts, and one of them revealed like, oh, this server's in an availability group, and people were telling me, yeah, but it's not really using that. And I'm like, but that's one of the differences between the servers. When I'm just comparing these things, this one says it is, and this one says it's not with these scripts. So what does that mean? And I haven't.
Try this. What if the storage that you've got isn't the best? So round numbers. Let's just say 10 milliseconds to commit a transaction and 2 milliseconds for network communication. If it's all local, 2 seconds, 10 milliseconds, 12 millisecond in and out. Okay. AG. 2 plus 2 plus 10 plus 2 plus 10. You go 12 to 24. Now stream a bunch of data in. You'll feel that. The other part there is just thinking, how much traffic do you have on the availability group itself with data changing? Because the SQL server might be struggling with the log writer between the two machines.
Well, they weren't actually, so like I said, I ran Glenberry scripts and it said it was part of one, but it's actually not actively being used in one. So I'm not.
That shouldn't be a problem then.
Okay.
You know, if it's set up with the same cluster, but there's no AG replication in there,
Yeah.
it shouldn't be any overhead.
Okay. It was at one point it was going to be, and then I questioned, like, hey, why are we putting that in availability group? This is a data warehouse.
Well, I mean, if it
Don't
can't
need
be
the
rebuilt
instance.
easily, I get it.
Well, the thing that somebody mentioned to me was like, if this region goes down, we got bigger problems in our data warehouse right now. So
That is true. Now,
they
that
weren't
said, if
too
you,
worried about that. Like we could probably restore a backup faster than.
yeah. Well, I mean, if you put it in AG and it's asynchronous and pushing to another machine in a different zone or a different region, that's not any extra overhead.
Okay.
Yeah, that should be fine.
All right. Cool. Good to know.
Yeah.
It's funny that you mentioned the ping thing because a long time ago, like I used to use ping for everything. I don't know why. I picked it up 20 some odd years ago. I don't even know. But is that a part of like normal speak? Hey, I'll ping you later. Because
Yeah.
apparently I've been using that forever. And several times in my life, I've had people come up to me and say, so I have to ask, what does ping mean?
Ping is normal terminology for us nerds in IT. You get outside of that, yeah, I end
Realized
up,
that. And I thought it was
yeah,
just like normal.
nope.
Like, oh, okay, let me.
I did that for my brother, and he just kind of went, hmm? He didn't know.
I used it in everyday conversation with everybody, and apparently, yeah, exactly what you said. It's not
Whoops.
known by it's an IT geek thing.
Yep. Networking terms, and I'll just say normal people, meaning non-IT folks.
Right, right.
They'll
Yeah,
who?
yeah, yeah. It's about what happened.
Yeah. So much fun. Yeah,
Yeah.
it's fun. But yeah, this is one of those areas where it's so foreign. It's so just dissimilar to all this stuff because terminology is different. The meanings of the same terms are different. You know, it's wild. That's it's honestly how we're in business. We're kind of this nerd Rosetta Stone punching bag between the infrastructure team and the infrastructure teams. That's most of my projects.
Funny you
And
say that because I just recently said, like, hey, you're using this terminology and that can be confused with this other. So let's
yep,
make sure we're calling the thing because it's really important.
yeah.
I hate to be, the one that says it. I
Well,
don't mean
you
to be
have
pedantic,
no,
but
you have to because I mean,
yeah,
calling an Apple a washing machine, you know, that could literally be as far apart the different terms might actually mean.
yeah, yeah, yeah,
Yeah, and they don't know, and
yeah.
we don't know. You know?
Like, I don't know what you're talking about when you say that term. Oh, you meant that. Okay, now I got
It's
it.
always fun. It's always something. You know, every day there's some new thing that comes out or some big thing changes, and you know, you start over on the terminology or have to retool and retrain. It's like I've been
Yeah.
doing a lot of conversions away from certain hypervisors onto others, and same exact term, three different hypervisors, three totally different meanings.
Oh, wow. Wow.
Yeah. And then you're trying to learn this at the same time you're trying to educate the folks that are there at the company trying to manage this stuff. And they don't know. And it's like you get into some terminology mismatches and it's fun.
Yeah. We're running into that with Fabric Link because
Oh,
people are confusing like shortcuts in Fabric because it's linking. So even in some of the Microsoft documentation, I was like, oh, when they're talking about a link in Fabric. They're talking about the shortcut. I meant the other Fabric link.
I'm letting all that just kind of shake itself down and settle in, because right now they're changing stuff faster than they're updating the documentation. You got 8 admin consoles for 4 tools to get 2 things to work, and it'll get there. I really believe it will. Right now, a lot of moving parts.
Yeah. Always a good time.
So much fun. Cool.
Well, thank you so much. As always, really love having you here. It's been a while, but so we're glad to have you back.
Thank you. It's always
Good
fun.
times.
Yeah, and if you're watching this on YouTube after the fact, don't hesitate to reach out. I'm a nerd. I just want to help fix stuff. And quite honestly, if there's an infrastructure-related database session that you want to see that we haven't already talked about, shoot me a note. Give me an idea. I'd love to write a session for you. It's a lot of fun.
Awesome. Thanks again, David. Have a great
You're welcome.
night.
Thank you. You too.
Talk to you later. Bye.
Bye.